Hello everyone, my name is Nailah Amanda.
My name is Raissa Anindra.
My name is Widya Pramudito.
I'm Rafka, Athallah.
And we are from BONAVENTURA team.
From class Calculus 1.
With Mr. Askar and Miss Sylvia.
And this is our material.
As one of the application of derivatives, related rates is a problem in which we know one of the rate of change at a given instant. So here's an example of what you might come across. d over dt of x to the power of 5 is equals to 5x to the power of 4 dx dt. And when you find d over dt of y to the power of 7, it is equals to 7y to the power of 6 dy over dt. So one thing to remember is that the numerator is d something according to the variable over dt as the denominator. With related rates, that's what you do. You're going to differentiate the equation with the respective time.
So the first step is to rewrite the equation of z squared equals to x squared plus y squared, and then next step is to derivate this equation. So that will be 2x times dz dt equals to 2x times dx dt plus 2y times dy dt. And then simplify the equation by canceling out all the two. So it will be z times dz dt equals to x times dx dt, and then equals to y times dy dt. And then the next step is to substitute the known quantities into this one. So it's gonna be z, because z is 17, so it's gonna be substitute with 17 times dz dt, which we are looking for, and equals to x is 8 times dx dt, which is 4, and then added by 15, which is y, and then dy dt, which is 5. And after this, calculate all. So it's gonna be dz dt equals to 8 times 4, which is 32, and then plus 15 times 5, which is 75, over 17. And the final answer will be 6.294.
Okay, hello everyone. Welcome back to me, Rafka, and we are going to solve a problem. So, a metal disc expands during heating. If its radius increases at the rate of 0.02 inches per second, how fast is the area of one of its faces increasing when its radius is 8.1 inches? So, we know that the area of a circle is pi r squared, and we know that the radius increases at the rate of 0.02 inches per second. So r to time, so 0.02 inches per second. And we also know the radius is 8.1 inches. So what we're trying to find is how fast the area of one of its faces increasing when its radius is 8.1 inches. So this is what we're trying to find. We can solve this by using the chain rule. dA over dt is the same as dA over dr times dr over dt. Now, we already have this, and we're trying to find now is this. So, the derivative of area towards radius, which is pi r squared. So, the derivative of this is 2 times pi times r. Since we already have this, now we can go back to solving it. dA per dt equals to 2 pi 8.1 times dr per dt 0.02. The result will amount to around 0.324 pi inches squared per second.
So what is the applications related traits in the real world? The first one is filling a swimming pool. Consider a swimming pool being filled with water. You can use related rates to determine how quickly the water level is rising in the pool concerning the flow rate of water from the hose. The second one is moving cars and distance. In a scenario where two cars are moving towards each other, you can use related rates to find the rate at which the distance between the two cars is decreasing. The third one is shadow length and time of day. As the sun moves across the sky, the length of an object's shadow changes. Related rates can be used to calculate the rate of change of the shadow length concerning the time of day. The fourth one is unfolding cardboard boxes. If you have a cardboard box that's being unfolded into a flat piece, related rates can be used to find how fast the area of the cardboard is increasing as the box is being flattened.
As seen on this graph, the function with the tangent line drawn here is almost indistinguishable in that little area, but as we get further away, the difference between them becomes greater. This observation is what we use for a method of finding approximate values of a function. The idea is that even though the tangent line isn't exactly equal to the final function, we can use it as an approximation for the function. So, differential itself represents small changes in a function, which helps approximate how a function changes with respect to its variables. Approximations using differentials are often done with the linearization process, where you use the tangent line at a point to estimate values nearby. It's a handy tool for making complex problems more manageable.
So differential approximation is purpose is to calculate without using calculator. So this one is what is the value of square root of 20? So the first step is to find the closest square root to 20, which is the square root of 16, which is 4 equals to 4. And then we have to derivate the equation of square root of x. So x is to the power of half. So it's going to be, if derivated, it's going to be a half times x to the power of minus 1 minus half. So simplify the equation, it's going to be 1 over 2 square root of x. So therefore, dy is equals to dx over 2 square root of x. So before that, we have to determine the value of dx first. So dx is going to be equal to 20, which is we are looking for, minus by 16, which is the closest square root to 20. So it's going to be equal to 4. And then we have to substitute into the dy equation, which is going to be 4 over 2 times square root of 16. So if we calculate these problems, it's going to be a half. And then the last step is to add y and dy. So y is 4, and then plus dy is a half. So the final answer would be 4.5.
Okay, for the next question, approximate the volume of material in a spherical shell of inner radius 5 centimeters and outer radius of 5.125 centimeters. So, we know that the volume of a spherical shell is 4 over 3 times pi times r cubed. And we know that the radius is 5, and we know that dr, or the subtraction between the outer radius and the inner radius, is 0.125. Now, with this, what we're trying to find is dv, or how to approximate the volume. So dv, we can first do that with finding the derivative of the volume towards the radius, like that. So we know that d per dr, 4 over 3 pi r cubed. We can change that to become 4 times 3 times pi times r squared. So we have this now. And with that, let's put it here. dv equals 4 times pi r squared, and then we put dr here because formerly the dr was here, but we're gonna put it here. And now we can just put in the numbers. So 4 times pi times r squared, which is 5 squared, which is 25, and also dr, which is 0.125. And once we multiply it, it will amount to around 39.27 cubic centimeters. And that's the answer.
What is the applications, differentials, and approximations in the real world? So the first one is economics and optimization. In economic analysis, differential approximation is often used to optimize mathematical functions that describe consumer, producer, or market behavior. Second one is industrial machine maintenance. In predictive maintenance, sensor devices are used to monitor the condition of industrial machines, such as temperature, vibration, and pressure. The third one is computer graphics. In computer graphics, differential approximation is used to calculate changes in pixel colors and lighting in rendering software. And the fourth one is financial portfolio analysis. In finance, differential approximations can be used to calculate the sensitivity of stock or portfolio prices to changes in economic variables such as interest rates or inflation.
Thanks for watching, guys!